So in this video we're going to analyze this double shear joint, and it is a double shear joint because we have this pin that's grayed out in the center, and the shear force is split across two cross-sectional area right there highlighted in red, and we can see where there is a force being carried to the right, and that force is measured 24 kilonewtons. So I'll just fill that in. So that's 24 kilonewtons. So what that means is to the left we would have 12 kilonewtons there and 12 kilonewtons there. And what we want to analyze here now is the shear force acting on each of the shear plane. We also want to determine the stress in the pin as a result of those forces, and we would like to know if the pin is suitable, the material for the pin is suitable, and if the material is not suitable, then how could we increase the size of the pin to ensure that it holds, or what's the smallest diameter the pin can be in order not to fail. So let's get into some analysis then. So part A of our question requires us to calculate the shear force acting on each of the shear plane. And this will be fairly straightforward because what happens is we have this 24 kilonewtons and that's going to the right. So of course that would be split across, as I said right there, in equal amounts because the forces must be balanced. So for each of the plane, let's say we call this at the top A, plane A, and at the bottom plane B, then the force acting on plane A would just be our 12 kilonewtons, and likewise the force acting on plane B would just be our 12 kilonewtons. So that's fairly straightforward already. Now the next part of the question require us to determine the stress, the shear stress in the pin. So that will require some more work, but there are formulas that we can use that will get us directly to the answers. And what we would typically do if you don't know the formula is to evaluate the area, the cross-sectional area of the bolt, and then we would do the regular stress formula, force divided by area. Now instead of finding the area of the bolt and then do force divided by area to find stress, I'm going to show you how you can use a formula that gets you to the answer straight away. So what that will look like here is we have stress equals force divided by area. But because the area that we have here is two cross-sectional area that the force is spread out into, we have to do 2A for area. Now the formula for area is pi d squared over 4, pi times diameter squared over 4, or pi r squared. So if we were to put that into our formula to say force divided by 2 times, say 2 times pi d squared over 4, then what you will end up getting after we simplify this, I'll just cut to the chase and show you what the end result will be. This will then give us 2 times our force over pi times diameter squared. And this is the formula that we're now going to use to substitute our values in to evaluate whatever the shear stress is going to be on one of the plane. So let's do that then. Let's evaluate our shear stress. So I've just cleared some space there to tidy up so we can clearly see how we're working. So to determine the shear stress in the pin then, so this is what we have. We will have 2 multiplied by our force. So that's our net force now. So it's the 24 kilonewtons, so 24 times 10 to the power of 3 that we want to use here, and all divided by pi multiplied by our diameter, which I'm just going to write now as a millimeter dimension. So that's 0.012 squared. And our final answer here is going to be 106 megapascal, or 106 million. So that's actually rounded. So that's the shear stress that's acting on one plane. And if you want to say verify your answer, then what you could do, you could calculate the area of the bolt, the cross-sectional area of the bolt, and when you get the area, you would then divide that by 12 kilonewtons. So we could look into that just to verify our answer and see if it's the same result. So to verify our answer, then we would have to find the area of the bolt. So this already is our final answer. This next bit that I'm going to do is just to verify, or in other words, do it another way, just to check if what we have here is actually solid. So then what we would have is area equals, I'm going to use the pi d squared over 4 method as well. So pi times 0.012 squared divided by 4. Now in meters, that will give us 0.000, so 3 zeros there, 1131 square meters. So what you would do with this now to check your answer is doing stress equals force divided by area, but you have to use 12 kilonewtons, so you have to use one of them force components there. So that's going to be 12,000 divided by our calculated area. So that's 0.000131. And lo and behold, we get the same answer, which is 106 megapascal. So that's the shear force acting on one of our cross-sectional area, and that corresponds with our previous answer. Alright, so let's look now at the next part of the question, which is part C. Let's see how we analyze this part. So for part C, we are told here that if the allowable shear stress for the pin material is 80 megapascal, we now need to determine whether the pin is safe or not. And for this, we really don't need to do any working out, because what's happening here is 106 megapascal is the actual, or the working stress that the material is experiencing, whereas this here we have 80 megapascal, and the 80 megapascal there, that is the allowable stress. So if we're allowed to have 80 megapascal and what we have happening is 106 megapascal, then it is safe to say that the bolt is overstressed and it is not safe. So as it is, this is not safe. So how can we make it safe now is what part D is asking us. So if the pin is not safe, then we need to find the minimum diameter required for the pin to achieve safety. So let's evaluate that now. So to evaluate the minimum diameter, I'm just going to go back to our previous formula, the 2f over pi d squared. And what I'm going to do here is we're going to rearrange this formula so that we have the diameter as the subject. And in doing so, we will get diameter equals all square root 2f over pi multiplied by our shear stress. So the question now is, which shear stress do we use? And the shear stress that we want to use here for this, instead of the 106, which is what we just used, we want to use the allowable shear stress, which is the 80 megapascal. So let's evaluate that then and see exactly what our diameter should be, and therefore making our material or our bolt safe. So we would have square root of 2 times our 24 times 10 to the power of 3, and all divided by now pi times our 80 megapascal, so 80 times 10 to the power of 6, and this gives us 0.01382 meters, or to look at it like for like, this is 13.82 millimeters. So you can see where our bolt at the moment is only 12 mil, but in order for it to be safe with our 80 megapascal load, or in order for it to carry up to our 80 megapascal load, the bolt then needs to be 13.82 millimeters. So that's it for this video. Hopefully you have learned something here, and if you have, then please subscribe to the channel and give the video a thumbs up, and I'll see you in the next video.